Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have lecture 5, and this is all about accelerators, or also known as graphical processing units. Some may even say we should put a GPU in terms of GPU, which stands for General Purpose Graphical Processing Units, because that's what we do these days. Although we inherited, let's say, the base technology from GPU and graphics and so on. Today we will see, as part of this lecture, realizes in a lot of different ideas of how basically this GPU technology was evolving to really specialized processors. If you remember, these are many cores, really not perhaps per processor the, let's say, cutting edge performance as we had in the CPU, but still lots and lots of them on a chip. And we will review this a little bit. But before we dive into the material of this lecture, let us review what we had the last time. And the last time was really all about shared memory programming. So we had the idea that there is this common shared address space that I can use, which was in the NUMA setup that you see here, the Uniform Memory Access, or CC NUMA, because it's a cache current, let's say, bus here interconnect that makes us feel that we have still a shared memory address space, although it's distributed. So in both of these setups, the point is that programmer can actually act that you see here. It can basically having a program access the memory, and then we would program it in a way that we read and write, of course, variables. But we have seen also in lecture 4 that it's not at all that simple. So there are different, let's say, ideas how you can protect critical regions, for instance. And we have also seen that the idea of race conditions around variables can, of course, cause conflicts, especially if you have, as this picture will show, and we had the last time, that you spawn these different threads. And that is all about OpenMP, the de facto standard for shared memory. And it will spawn different threads to do, work in a certain parallel region. And this could be 3, could be 4. Here's an example. We had also understood that the master thread was sort of special. It always remains basically to give, in a way, the whole program a lifeline, right? That is a bit like this gray stuff here. But every now and then it will spawn different threads to help. Could be a loop, as we have seen last time. Could be different sections, or even different elements where we have functional parallelism, maybe, where we say, okay, let's divide it by the idea that we get as a thread ID. Let's do different things. And this gave us the analogy also that you see a little bit here on the top right already. So we have a way, almost like we had in MPI, to understand our identity as thread, right? So T0, T1, T2, T3. So we have, it is not called rank, so don't be confused like this, but it was similar, like basically the idea that we had in MPI, if you remember, and based on these ranks, we could do different things in MPI. And in OpenMP, you have sort of a similar idea. The environment of OpenMP gives you essentially not only how many threads are in a parallel region, but it also gives you then a unique thread ID if you want for all the different threads, which is also then an important differentiation. So here we talk not about a whole fully fledged process that we had in MPI. Here we talk about lightweight threads, if you will, that really then perform something in parallel. And this something is now an interesting way of programming that you see a little bit here with the Pragma Sentinel and with the idea of instrumenting the source code that is there. So in a way, when you think about back MPI, where we explicitly programmed message exchanges right here, and we did this in parallel. We did this with broadcast. We did this with, the ping pong, if you remember, send, receive, and so on. Here, we don't really touch the source code itself. We rather give the source code some, let's say, augmentation. This could be done in parallel. And this is a different way of really, implementing parallelism here. Of course, it can still work very similar, like you have here, for instance, you see, this hello world, which is the trivial example that we have shown the last time, hello world access, but then when we execute this, we have just 4 times hello world, because we basically have this parallel region automatically created by the pragma statement that is covering only the printf statement. So an important other thing was, if you remember, that we could steer the number of threads from the outside. And this is export OMP num threads. So this is something which you either put in the environment, or you have seen it here in the job script. Of course, the environment then is digested from the scheduler. And the idea that you see there downstairs was just an example to show you a very large source code, really, that is far away from the hello world. So it's a really scalable and parallel and scalable clustering algorithm that was implemented by one of my PhDs in the past. You see here the publication that also have references then to the source code. And you really see that essentially this is possible to do in shared memory. But of course, we sort of learned also with several different examples that you basically don't scale with shared memory, right? So if in order to have really large real problems, real life problems, you really need to go also the MPI way, and that then bringing us to this hybrid MPI and OpenMP, right? And we have seen some performance plots, if you remember, that by doing so and doing the hybrid, in other words, what does it stand for usually? OpenMP within the node, right? Leveraging the fastest I have in terms of memory access, which is limited, but still fast. And then I combining this with distributed memory across the nodes with MPI message exchanges. In previous lectures and basically iterations of this course, we had also a complete lecture on hybrid programming. I don't do this anymore because we have, let's say, new technology GPUs. It is all about today, for instance. So, and we cannot cover everything in the code and in the whole course, really. And this code, however, is interesting for you to look at because it combines MPI and OpenMP, and there's a real life, let's say, algorithm that is there. And by now, it's basically the most scalable and parallel one in terms of DB-scan, which is one of the algorithms that is out there. So correct me if I'm wrong, also to the YouTube audience. If you know anyone that is scaling better, let me know. There are different approaches, but I think my PhD student here, we have done really good job of doing this. Hence, it's still used and a practical algorithm. But let's come now to the next step when we talk about lecture 5. So this is more a sort of conceptual lecture again, right? Because MPI will be part of assignment 1, and OpenMP part of assignment 2, and then we do a bit of deep learning and so on, and you know, assignment 3. But we have some conceptual topic first, because we will see that in deep learning and parallel and scalable machine learning, the role of GPUs is now legendary, I would even say, right? So it was lots of advancements, and it's fascinating to talk about this because, you know, and you will see in previous iterations of the course, I had cutting edge technology saying Volta 100s. Then I said, okay, we have now the Ampere technology, Ampere 100. Now, recently, last year, I talked about basically Grace Hopper 100 or Grace Hopper in general, the next iteration. And now we are Blackwell. So next generation. So you have here something which is extraordinary, I would say, in high performance computing with this massive, massive increase of technology, you know, being available also. So it's really interesting to see that this evolution, and with this, the fast pace of this technology and its adoption has a profound impact in HPC at all, and also at applications, as I will show. And of course, deep learning, distributed deep learning, but not only data science and deep learning can really benefit from it significantly. So what I'm talking today is sort of several updates to the lecture we had last year, but not many. I think some of them, of course, are still the top 500 list. Obviously, there's a new top 500 list we will talk about. We will shortly review again the multi-core versus many-core, but by now everybody should have that hopefully in their mind. There are certain terminologies which you hear always when you say, it was a Kepler, a Pascal, a Volta, so that you know a little bit about these NVIDIA architectures, although I'm not paid from NVIDIA, but they have a dominant market share in one respect. But we will also see when we talk about the new top 500 that is just out there from November 2024, Cray and AMD with so-called Instinct cards actually following suit and have, let's say, even the top 2 or 3 systems in the top 500 that are actually not anymore NVIDIA, but actually Cray. And we will talk about these different ideas and then come quickly to the idea of really high performance computing, because many of you will think I still need my workstation. I put one GPU in and I'm happy. And this is not what we call HPC. Hence, we have to talk about so-called node architectures. And I would like to demonstrate something which is a bit, let's say, older in the summit, but it was very well, let's say, documented. And it shows you also a generation of a HPC system which was cutting edge 2018, so 6 years ago, up to 2019, 2020, you would say #1 in the lists. And in 2024, decommissioned because basically V100 cards, not cutting edge anymore. So time for the new system, Frontier. And it shows you very nicely this generations of technology that influence also the bigger picture of the generations of HPC systems, which at some point in time, are decommissioned. You remember in one of my earlier lectures, I gave you the Blue Gene examples, right? Which was basically Blue Gene L, Blue Gene P, Blue Gene Q systems from IBM and Lenovo. And at some point in time, the whole series just stopped. Another good example of this quick evolutions really of technology. So we talk about this a little bit. Also with a very nice understanding how research goes along the way. So because we have seen islands of NV links and NV switches, and we talk about what we mean by islands. Essentially, you can say you cannot scale up to very many nodes. So there was lots of research done how you could leverage the so-called GPU direct interface. You have seen the examples in deepest. I come back to this with modular supercomputing, why our booster has so many GPUs, but very, let's say, low performance CPUs, because in the end, they don't really matter for GPU intensive load. But we need to have them because we have host CPUs still, at least in the older generations. And of course, we will quickly review Elia. What do we have in HPC in Iceland in this Elia system? The second part will be then, basically after a short break, much more about uptake, usage, right? So where are the programming models? We talk about CUDA here a lot because it's NVIDIA again, but also AMD Instinct has its, let's say, ROC toolkit. It has different technologies. We see new vendors coming with Intel. And there's also some standardization going on, although we see still a dominance probably of CUDA code in the accelerator business. But this might be something for the future where we have seen already in shared memory, the OpenAC, for instance, and also the HIP interface. So hence, this is a very short briefing of GPUs. And in one respect, I think we are at the time that I could teach a whole course on GPUs, right? So I think that's now the time, maybe already in the last couple of years, because there's so much to know, to understand. Things we just not really cover fully is the HBM, high bandwidth memory, which has a profound impact on GPU. So how much you fuel the computing with data and sort of things which I not can cover completely in detail, but it's an interesting, let's say, lecture. I hope still to give you an overview if you want about this tech, let's say about the GPUs. And if you really want to go deep into this, for instance, do your own CUDA code, then of course you have to go to some of the centers or to the EuroCC competence centers. They have probably some courses or experts that can also teach much more about this that I can here actually cover in this HPC course. All right, so after this, you have another aspect of parallel programming, really, which is relatively complex. Accelerators, there's also this HBM I mentioned. You have the NVLink, NV switches, different evolutions of GPUs, tensor cores. You will have lots of terminology, quite complex aspects with an enormous pace of technology advancements. But really, when you master this lecture, you really have also a good overview how parallel computing is done today, really by leveraging the so-called accelerators, which is a term essentially standing for a broader aspect. So in the future, we maybe could even say a quantum device might be an accelerator of sort, right? So alongside GPUs for different other problems. So this is really a different programming paradigm that you really, have to understand and use instead of, for instance, using MPI, OpenMP before. And you will see, luckily, there are already lots of libraries that have implemented elements in CUDA, so we can simply use GPUs. Still, here and there, you have to do data loaders for deep learning and things like that. So things I will also talk in subsequent lectures, but let us review a little bit now the GPUs. And I will start again by the multi-core CPU. By now, you know cutting-edge performance, high single-thread performance per core. That's not what a GPU is. That's why we call it basically a multi-core CPU. And you know the limits. We cannot do more and more on the chips. We had this also in lecture 1, so I go a bit quicker here. The solution that then was suddenly there derived really from the idea of graphics, right? So here, you know, many of you at least have probably used the NVIDIA GeForce for gaming. The gaming industry was really strong, pushing NVIDIA to its limits. And still, this is not directly what we do now in high performance computing. So we use this as a general computing. But interestingly enough, we have seen that many of the examples that we have, not only in scientific computing and deep learning, also in many other problems require, let's say, every time execution, which is nicely parallelizable. We talked about this data parallelism, task parallelism, a little bit in lecture 3, you know, about the other concepts. And where, you know, even if it's, let's say, not so cutting edge computing, we just need very, very many of them, thousands or so in operations. Hence, the idea of this many core chip is to have this cores really in a moderate performance level, but really have thousands of them on the chip. And with this, the chip is not getting too hot and works. And the general purpose is now coming to the idea that, of course, we leave the realm of graphics. And with this, you know, different programming models emerge and so on. And I would like to give you an example, which is quite interesting because it's something what we had already before, that is, of course, interesting for deep learning because we learned already there's matrix multiplication, matrix vector multiplication. They have this color code here in computing, and they're nicely parallelizable. But here I want to give you also another example of AMBER. So AMBER is a molecular dynamics code, very popular, also decades of developments, you know, interaction of atoms and so on, energy, force fields. I would say it would be rather the area of simulation sciences, physics, right? But they still have the power, basically, in this application package to leverage then, let's say, different GPUs instead of CPUs. So hence we're talking about a code that was used in parallel computing since a long, long time. And even those, let's say, non-deep learning codes, and this is now the point in it, right? Also simulation sciences, those that are driving physics, and also the second part of the course with the short lectures, Reza will give you overviews, you know, in different areas of sciences, mostly, of course, with CFD, but still giving you examples where GPUs are more and more used. Hence, it's not only deep learning and not only machine learning that benefits from it. We see now, and I will come to this also during the course, many different implementations on CUDA that leverage this many core idea. And we skipped a little bit the idea how now this looks a bit more in detail, and then also the sort of generations. We always said, well, the GPU is like this and fantastic, it can do many core. So what I want to bring across with this lecture here is really the massive pace I told you in these different areas, you know, that we had in GPU programming. So first of all, the number of cores you see here in one of the earlier let's say, you know, cores, and if you want the whole chip. But you also see, quite interestingly, the performance here when you do, for instance, an AI training on large models, how significantly, firstly, the generation makes an impact. And here we're talking, for example, you know, the switch from the Volta architecture to the A100, right? So this is basically already quite some speed up, but and now it's a point that we have also then the idea of the memory alongside. And because we talk about often data intensive computing, data is a very important factor on this. Hence, we have here from the A100, this 80 gigabytes, quite an interesting speed up into, should mean that basically through all this architecture generations, really, right? When we talk about Fermi, Kepler, Pascal was often used, P100s, Volta V100s, A100s, and now we have even Grace Hopper and Blackwell. And we come to this. But it's not only that the number of cores change, much more cores, also the HBM, the memory, all was going alongside, and also with it a little bit the idea of computing, let's say, not the full floating point precision, right? You see FP16 and so on, and you will see several tensor cores that will have then very dedicated cores to do computing for, let's say, specific workloads. As the name suggests, with tensor cores, you're already in the area of tensor. This is a fancy name for a multidimensional array, really. So basically, here we talk about, again, support for deep learning and so on. But as I said, also this can be used by many different other scientific packages. And here you see some generations of the past, AMD Radeon, that's not anymore really, let's say, the GPUs. We have now Instinct cards, which are really good. But it shows you also over a long course of history how this basically has been developed and from different vendors, really marking then that by the time when we had the P100 and V100, it was pretty clear that there was a large, let's say, market share going to NVIDIA. And this is continuing still with the Grace Hoppers. It's still continuing probably very soon now with the Blackwell, the new architecture. However, we will see also some examples where we then come to the point that we have AMD now, also catching up with Cray and Instinct cards. So you see also here how it works in different areas of sciences. That's why I brought these examples. So this means we leave the idea of typical AI, right? So these are lattice, QCD, genomics, climate modeling. These are all physics, let's say, driven models. You also see the impact, which is quite interesting, of this NVLink network. I want to make a case in this first part of the lecture as well. We talk about high performance computing. That means for us, one GPU is not enough, right? Otherwise, we put it in a workstation somewhere in a desk, and that's, a workstation with a GPU, not a HPC system. Hence, we want to interconnect, right? As you would probably imagine, many of those cards, very many, to really do a high performance computing system and being able to scale. And what you here quite nicely see also then the impact when you have a specific network that is supporting this with the H100, which is already quite cutting edge performance. And you have this in language model, GPT-3 and so on. That doesn't matter so much, but you see again, given the NVLink network, this has also quite an impact in several of the applications that are communication intensive. And hence, our top 500 looks now quite interesting. We can imagine that all of the key systems here in the upper part of the top 500 are now fueled by so-called accelerators from different vendors. The top 500 is an extraordinary important list for supercomputing, for HPC in general. It has always every year, basically twice, release, if you want, where you always see the top-notch systems. In the last year, I could actually already talk to you about an exascale system coming into the list, and then now suddenly we see a complete different approach again, especially if you now consider that NVIDIA was quite strong in the lists a couple of years before, and now we see really the entering of AMD Instinct cards significantly. El Capitan, Frontier. Frontier is a new system from Oak Ridge, which actually was superseding in a way Summit, right? So the one I want to talk about too, being decommissioned, and now Frontier is a system. And it basically switched from V100s, which are in Summit, to AMD Instinct cards. You see also different generations of the Instinct cards. This is also no surprise if NVIDIA has several generations of GPUs and technology. Of course, AMD cards are similar in the sense that, of course, they always have an evolution. And you see here also the special Fujitsu architecture, which was quite known and quite, let's say, on the high end here in the upper system part, is basically now coming a little bit lower and lower in the list because there are more and more new technology really. You see also that even if you maybe employ cutting edge systems in the Instinct MI300 cards, you may be not still in the top 500 or number one. The reason is, of course, also money, right? Now, here we talk about technology that is extremely expensive. right? Hence the high performance computing systems are multi-millions of investments. And hence also a big market and lots of payments for, the vendors again, which makes this interesting to see what are the vendors and also what are the accelerators, right? Which are basically having the system share. And there's also more and more changes given AMD is basically coming into the game more and more with the Instinct cards. And also, of course, the new generations of the NVIDIA H100s, for instance, and also depending on the, basically memory setup. So it's quite a lively list. I encourage you to test it out, try it out, go to the top 500 list and play around with what you can do in terms of statistics. It's quite interesting to see the impact of GPUs in generally today, but also many other players and so on, like in the vendors. So let's look a little bit on one example, which I found captures the essence of high performance computing, for me in 20 years now. So I have been, starting with a jump system in Jülich, a very, let's say, constellation system of IBM, power architecture, and suddenly the time was over. And then we had the Blue Gene L, P, Q. There was an example, for instance, of a more scalable solution, and suddenly the time is over. So now we have Jewels, we have Eureka, and soon we will have Jupiter, the first exascale system in Europe. And at some point in time, probably Jewels and Eureka will say bye-bye. So it captures the essence of HPC systems being always on the cutting edge of computing. And now when you talk about Summit, we have to see they dominated the list in 2019, 2020, something like this, and 2018. But then, of course, thinking about that, there was still V100 GPUs and very many of them. So the fascinating story was it was 6 GPUs from V100s on one node. And then, and you see that a little bit here, it was 4,000, 600 nodes roughly of 6 times GPU. So we talk about 27,000 GPUs. So this is the realm of high performance computing. And we want to use them. And some of the codes even scale that high so that you can actually use the whole amount of GPUs for real scientific problems. Needless to say, this has impacts in terms of megawatts. So what terms of, power you need in order to drive such a system, but also on the space, you can imagine already from the space here, we talk about 2 football fields, or if you want, there are maybe more 2 tennis fields, right? But this is also huge halls full of computing, densely connected cards with nodes where you see 6 GPUs are very densely packed on one node, and this is amazing. But now the time has come that, basically Summit is decommissioned from around actually last year, November, something like this. So just to give you also an overview now, that from 2018 cutting edge, 2019 cutting edge, 20, we talk about 4 years, 5 years, right? That now Frontier is there. And we have now, instead of petaflop performance, exaflop performance. So this is another, exascale system, which is now with 1.6 exaflop, one, big system. But you have seen El Capitan is even bigger and bolder. So we have the cabinets, which were very many at that time, but now much more densely with this is 74. You have the switch from 6 NVIDIA Volta, right? The V100 cards, 6 per node, to now basically this interesting new 4 AMD Instinct cards. And you go on and go on. Basically, you have this Infinity Fabric, which is similar to the idea of the interconnect, right? So CPU, GPU interconnects play a big role, as we discussed, to really scale up to more than one node and, to go across different nodes, and with NV switches then bigger and bigger. And I will come to this in a moment. So hence, let's look a little bit more on an architecture where we now leave the space of one GPU, but talk about a HPC machine. And I think Summit again captures the essence well. Even if it's V100 cards, don't worry about this. It's still, I think, a good overview of the architecture, which I like here. So you see clearly the Power 9 architecture here, CPU still required to drive, let's say, the whole system design. But per node here, we have 1, 2, 3, 4, 5, 6. And here also basically GPUs that you see here. And each of them, this is, 3 GPUs and this is 3 GPUs. So of course, this is one node with these together. So, and you see a little bit here also the HBM, so this high bandwidth memory I was alluding to, and why this is an interesting figure is that shows you really the gigabytes per second, 900, right? So which is quite impressive, but we will see soon that the next generation is even better. But this is already something how you fuel basically data to the GPU. Still, you basically at that time also a bit limited that you have to always go through the host CPUs a little bit, right? So we talk about this more in detail later on. But this is sort of a node architecture. And of course, each of the typical CPUs have also their own memory that helps. But you see also the bandwidth to the memory is 170 gigabytes per second, while we talk about this high bandwidth memory, as the name suggests, high bandwidth, 900 gigabytes per second. So a complete different order of magnitude, but limited because we in the end have just fueled it to one GPU. And we have to go, of course, if we now want to exchange data with others, distributed deep learning needs this, for instance, we will talk about this in lecture 6 and 7, then we need to leave the node. And we leave, basically to much less performance than this 50 gigabyte per second. And you see here a little bit the role now of the so-called NV-link, that you have the links where all of these are actually connected with each other to basically have the GPU interconnect essentially in one node, right? So this is the idea to have now, per node really good, possibility to use more than one GPU. And you see this quite nicely in plots. But again, the trouble is we are staying in this node, but we want to go across nodes, right? So hence the full bandwidth there is also not anymore achievable. Hence there was lots of research done, for instance, in the D project I was alluding to earlier, for instance, how you can basically go around a little bit the problem that you have that essentially you have this bottleneck and had it for a long time, that the CPU is, basically having very good memory and relatively good bandwidth, not as good as, of course, the memory bandwidth we have seen, the high bandwidth memory for the accelerator. But the achievable point is that you have to always go from the host CPU memory to the device memory. And this was sort of always a little bit a problem. And then, of course, when you want to interconnect, then different cards coming to another problem. Hence, this influenced also a little bit the design of our booster that we had. If you remember, basically in the deep architecture, the booster had many different CPUs, which are not cutting edge, and powerful GPUs, because in the end, we were just interested in the GPUs. And this also suggests a little bit an idea of how you can use a CPU as an interconnect device or as a communication device instead of, doing much computing on it. Then a couple of other facts. Something called tensor cores is another terminology I just wanted to share here. What's up with this? In Pascal, you had basically different precisions where you basically started with a floating point 32. So really, let's say precise computing. But then people found out with floating point 16, this is still much more faster, obviously, but also has a good effect essentially on deep learning, because in deep learning, we have anyway, let's say, not the accurateness that is so important in this, but rather the throughput. And in some studies, even it shows it has a certain regularization effect to not take any data part by heart and all the details. So this is basically something which we will also pick up a little bit in later lectures, right? When we talk about deep learning, that in the end, we don't have precise optimization process and so on and so on. And for this, the tensor cores were quite good. And even now, some of my students like Marcel, also recently graduating, are actually experimenting even with less precision, right, these days. So this is an interesting effect that came, and then motivating a bit this new tensor cores and why you have done this. And of course, you see here the deep learning training in one workday with this new cards that have then this tensor cores. You could significantly reduce essentially the time to solution, which is one view here. Or you basically see here again, the generation change from Pascal that you see here without tensor cores to the V100 architecture with tensor cores. And this is just one part of it. What we now have is a little bit that in high performance computing, again, always the idea with scaling, so scaling to much more nodes. And even if we have the NVLinks that we discussed from NVIDIA there, and they're actually quite strong in terms of gigabytes per second. Of course, it's not like HBM, but still we're leaving the memory space and have an opportunity to have inter-GPU communication. But still, we talked about a long time in research also that this is certain islands, right? So where we can maybe have just 16 GPUs per service, 8 GPU pairs, where you come to the perspective that we need something bigger, and this is where the NV switches came, because they incorporated then sort of different NV links to have really an all-to-all GPU communication, and then basically making the single node sort of perfect. But then again, the problem is scaling very high in the number of GPUs. You have seen Summit with, let's say, almost 25,000 GPUs. We want to use them all together. Then you come into some certain effect that the NV links and NV switch islands would not help you anymore that much. But technology advanced. And of course, I mean, we're not talking about that as everything is very simple still to, let's say, use a system like Summit with 25,000 GPUs. But you see interesting new related technology evolutions. Also, the fast evolution here, I want to show you of this NVLink, right? Because we have learned in HPC, we really need the interconnect between the different GPUs. So in this sense, you see here the Pascal again, and then the gigabyte per second that you had really as throughput, the NVLink and V100 was a big step going to A100s, and then basically the Hopper card, which was recently basically the cutting edge, if you want, of GPU architecture. But now we have the 5th generation, basically with this new architecture, which is fascinating. It's a Blackwell architecture where we will see many interesting new elements happening. So hence we will see here a little bit also that not only, of course, the bandwidth improved, also the maximum number of links per GPU, right, which was driving a little bit the Summit design maybe. But here you see now we have 18. Or as we have NV switch GPU to GPU bandwidth, right? We had this 900, 600, now we have 1,800. So it is really, let's say, a massive improvement in the bandwidth, which is in HPC applications now a major impact, right? Especially because we go now, to much more different workloads and so on. And with this, we have really powerful NVLinks and NV switches. And I mean, we can imagine that this will continue, right? So the evolution of this technology is really fascinating and fast. And coming then back to the idea that we had in deepest, right? So when you now think that this is so much quick, and the idea that was there in this project, for instance, was to use the host CPU. You see that a little bit, and we will talk about this offloading a little bit, let's say, in the second part of the course more. Although in some of the GPUs today and in the workloads, you have to seriously reconsider this. But here the idea is that normally you have a CPU, right? It normally does computing. It will use data for uploading from the own, let's say, memory and the compute node to the GPU, to the accelerator. Then there's a kernel executing in the GPUs, and the results are downloaded again to the MPI, to the compute node. And then you communicate this with MPI to different nodes, and then the story continues and so on. And here you can basically see the idea of more and more, let's say, typical way of doing CPU GPU offload, right, to this. So one of the ideas in deepest was then instead to really don't compute anymore on these. And this drive was driven a little bit also then by the idea of the booster, right? So the booster, if you remember in one of the earlier lectures, I said it has relatively weak CPUs. So I mean, still okay CPUs to get everything, but there will be no computing on it. So if you want, you see that here a little bit with no compute, you're in essentially doing a little bit of MPI for communication exchange to get the results and the data directly from other GPUs into the kernel, right? Using this. So in a way, you use it only as a communication device, the compute, interface, and hence you don't need the full-fledged CPU, saving costs in a way so that you can basically employ more GPUs. And this was going against the NV links and NV switch islands. But now we see, of course, more and more that these islands, getting very powerful and bigger and bolder. So also this design has to be, revisited. Then finally, for today, just a short hint, of course, our systems in Iceland are, let's say, limited. A small country has also a small HPC system, but we have, GPU cards. And not forgetting that we, of course, are also a member of the EuroHPC joint undertaking, so we can have also proposals to be submitted to the larger systems. But our local system here in Iceland, where you see also different elements you have now learned, has a partition of A100 cards, 3 of them, for instance, and also another dual GPU card where we have 2 A100s. And basically 5 times this dual card nodes. Hence a little bit limited GPUs, but of course also technology in Iceland for users that need to do it. And maybe finally for you at home to understand as a good quick summary, I like this video a bit. It's really showing you sort of the difference between CPU and GPUs quite nicely. So I encourage you to look this video. I will play it now. And we will do a short break and we'll continue after 10 minutes. So talk to you then.